Okay, today's lesson is about, hold on to your hats. When your calculus teacher says hold on to your hats, it is not idle chatter. Hats, hold. The fundamental theorem of calculus. Part 1. Yes, it is important. It is fundamental. There are fundamental theorems of almost every branch of mathematics. Fundamental theorem of calculus is huge. It is the big one. Okay? There's the fundamental theorem of arithmetic that says every number has a unique prime factorization. That is huge. Your internet security is based upon the fundamental theorem of arithmetic. No fundamental theorem of arithmetic, no internet security. Because it's all prime numbers. Okay? The fundamental theorem of algebra says you have a polynomial with real coefficients. It has solutions. Real and or imaginary, but it has solutions. That is a big deal to know that every polynomial has an answer. Being able to solve a problem, knowing that you can solve a problem, that's huge. Part 1. If f is a continuous function from a to b, then the function f of x, the antiderivative of the original f, from a to x of f of t dt has a derivative at every point x in the interval a to b, and the derivative of f is the derivative of the integral from a to x of f of t, which is f of x. And yes, there's a lot of f's in there. Get over it. It's the way it's written. It needs to be written the way on purpose. A is a constant. A is any constant. Okay? A is a constant. A is any constant. So basically, it's the big part is the derivative. Getting down here to the bottom, the derivative of an integral from a constant to a variable is the integrand, the function we were taking the integral of, at that constant. At that variable. The derivative of the integral from a constant to a variable is the function we're integrating at that variable. It's a very easy derivative to take. You take whatever this function is and you plug in x. Okay? Very easy. A couple of people are still getting this down. I'll let you get it down. Down. Okay. You don't have to necessarily get this written down, but do please pay attention. It is hard to underestimate the power of this equation. It says that every function f is the derivative of some other function, namely the integral. Every function is the derivative of another function. Every function is a derivative of another function. That's big. It says that every function has an antiderivative. Every function is a derivative. Every function has an antiderivative. There's something before it. There's something after it. Every function has a derivative and an antiderivative. And the last thing that's really, really important is that the process of integration and differentiation are inverses of each other. Integration and differentiation are inverse functions. That's what this part says. That's what makes this so strong. That one little statement, this one little equation down here at the end, this little equation down here at the bottom basically says 3 important things. Every function has a derivative, every function has an antiderivative, and derivatives and integrals are inverse operations, because if I take the derivative of the integral, I get my original function back. That's what that says. Okay, so the concepts are huge. It's a simple idea. It's a simple statement, but it's very, very big things, very large ideas. That's part of what makes this so big. Okay, that's what makes it so huge. Okay, now, applying the rule. Because you have to learn how to apply the rule. How to apply the fundamental theorem, part 1. Basically taking derivatives of integrals. Okay. So the first one, find the derivative of the integral from 3 to x of negative cosine t dt. Okay. Remember, it's from any constant to x, to essentially any variable. Big thing is the variable in our upper bound and the variable here need to not be the same variable. That's the only thing you have to have. Okay. Has to be any constant, and it can be any constant. That's easy. Negative cosine x. Yes?
Would it ever be the same variable?
No, it won't be. It won't be because the rule doesn't work with it being the same variable. So, yeah. Any other questions? Yeah, I know you're looking at it, you're going, oh, that can't be that easy. I know that look. That look is. Okay, you're just waiting for the other shoe to drop. I can tell. Well, guess what? It's going to happen. All the other things that happen are all twists and turns on this basic concept. And we have to go back to our rules of integration. So, example number 2, we have an issue. Our lower bound is the variable. In our statement here, come on, one more. Lumos, come on. There. Okay. Our lower bound was the constant, our upper bound was the variable. So if we go back here, we've got that reversed. But we have this nifty little thing that says we can flip it at any time we want to flip it and just make it negative. So this is equal to the derivative of the negative integral from pi to x of 1 over 1 plus t squared dt. Because we have a rule that says, oh, hey, if we want to flip the bounds, we can just flip the bounds, just change the sign of the integral. And now we can take the derivative, and now we get negative 1 over 1 plus x squared. That's it. I must be doing it right. There you go. Okay? Use your rules. Use your rules of derivatives. Okay. Can you guys read this one? Can you read the equation? It's a little dark. It's okay. I tried to make it bigger too. Okay, so y is the integral from 0 to x squared of sine of t dt. Find dy dx. In other words, take the derivative of the integral. This is just another way of doing the same thing we did. Take the derivative of the integral. But we have another problem. Our lower bound is a constant. We're good. Our upper bound is a function. Not just a single variable. On the previous examples, just a single variable. Now we have a function as our upper bound. A function in terms of x. Not a problem. Chain rule. This is a chain, becomes a chain rule problem. To take the derivative, you still dy dx equals, still plug the upper bound into the function, the sine of x squared. However, because it's not just a variable, I need to take the derivative of that function. What is the derivative of x squared? 2x. Now, we want to make it look pretty. Dy dx 2x sine x squared. And I know some of you are probably saying, okay, but what about the plus c? We don't need to worry about it here, and you'll kind of understand why when we get to the next step. Because we're doing it actually evaluating of sorts. And we're not technically taking antiderivatives. Okay. Ooh. Uh-oh. Do I have any constants at all? No. Well, we have some rules that can help us out. Okay? Go back to your properties of integrals. I can separate one integral into two integrals. Because we could take two integrals and combine them up into one, right? We had a rule that said that we could do that, or a property that said we could do that. And if we can combine two into one, that means we can take one and separate it into two. Y equals the integral of 2x to some constant of 1 plus 2e to 2 plus e to the t dt plus that constant to x squared of 1 plus 2e to the t dt. Remember, we have a rule that says that we can just go ahead and separate it out. We can combine two up, we can break two up, as long as the upper bound of the first one is the same as the lower bound of the second one. So you split it up into two. We did this in some of your practice. Oh, we got to screw around with this one here. I'm going to cheat in my writing, make it negative and change that to a, and that to 2x, because I have to have a constant. But that's all you have to do. Just flip it over and change the sign, and you're good to go. Plug it in. dy dx equals negative 1 over 2 plus e to the 2x times the derivative of 2x. Because you got to do times derivative of what you're doing. Plus 1 over 2 plus e to the x squared times the derivative of x squared. Chain rule. And we want to make it a little prettier than that. So put negative 2 over 2 plus e to the 2x plus 2x over 2 plus e to the x squared. And there's not really a whole lot you can do to that. You can't divide by 2 because only one thing in the denominator is divisible by 2, not both of them, right? They have to be both. I've seen it where they'll pull out a 2 and have 1 plus x and try. Yeah, it's not worth it. Let's leave it alone. And that's it. Okay. I don't want to get, once again, it is simple. There's not a lot going on here from the standpoint of what you're doing, your applications, and applying the fundamental theorem. But the concepts that come from that one statement, every function has a derivative, every function has an antiderivative, and integrals and derivatives are inverse functions of each other. One undoes. You take the integral of the derivative, you get the function. You take the derivative of the integral, you get the function. Knowing those things really is very powerful. Very, 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 very powerful. We will do part 2 mañana. And part 2 is really, really going to be a lot more useful to you than what we're doing.